Welcome back to the module on dynamic approaches for AutoML. In this unit, we're going to talk about dynamic algorithm configuration. Now, dynamic algorithm configuration, or in short DAC, differs from the prior approaches in that it produces a policy and not only dynamically tunes, right? So PBT, we have seen, can produce very well-performing models by dynamically tuning, but you cannot use the schedule to tune across related tasks. You are really locked into that, and all you get is a very well-performing model. You might be able to observe some trends, but you cannot really use those trends in a dedicated manner to optimize a new neural network on a very similar task. So DAC really wants to have reusable policies that adapts the hyperparameters. And the key here really is reusable policy. Now, let's be a little bit more formal and define the DAC problem. So first off, we need a hyperparameter configuration space for an algorithm that we want to configure. We also need a probability distribution over data sets or tasks, since we want to really have a policy that is general and allows us to tune hyperparameters across tasks. We also need a state description of the algorithm, solving the particular task at hand across multiple time steps. And we want an associated cost metric that tells us the cost of the configuration policy while solving these different tasks. Now, if we have all of these things, then the dynamic algorithm configuration problem is to obtain a policy by star by optimizing its cost across a distribution of data sets. And again, distribution of data sets is key here. We want to have something that is not just applicable for a particular data set, but we want to have something that is flexible and general and can be applied across multiple data sets. Now, we can also formalize DAC as a contextual Markov decision process. And this formalization is very important for some of the solution approaches that we will see in this unit. Now, for a contextual Markov decision process, we need a state, ST, that in the DAC setting is just the statistics that are gathered in an algorithm run. So this could be, for example, the depth in the search tree already. We need an action that determines how to set the hyperparameters or how to update them, right? So we could either directly set the values of the hyperparameter at every time step, or we could just adapt the previous hyperparameter similar to what PBT does by perturbing it slightly, or by saying, okay, we just add this certain delta, increase it slightly, decrease it slightly, and have a more flexible temporal structure here. We need a transition function, and that in the DAC setting is the iteration of the algorithm for one or a few steps with the given hyperparameter setting, so that we know that with the particular state of the algorithm and the particular action at this time state, if we run it for a step or multiple of these steps, where do we end up in terms of the next state of the algorithm? And we need a reward that is the current cost or the approximation of the current cost. And if we have a reward, right, we can also use that to directly optimize for this reward. So maximizing the reward to get the best out of our configuration schedule. Now, very crucial here, it's not just a Markov decision process, but a contextual Markov decision process, because we want to be flexible and general and solve for multiple data sets, right? So the context here for which the policy could be operating on this Markov decision process is the data set at hand, because it has implications of how we transition from one state to the next. On a much simpler problem, right, we might be advancing to the goal state much quicker than on a harder problem. I want to recall here that can be done by heuristics, and I want to recall this here because I wanted to highlight with this cosine annealing example that heuristics, while they are very great in providing community knowledge and giving you a direction of how to dynamically adapt your hyperparameters, they come with their own hyperparameters. Right here in this cosine annealing example, you need the initial or maximal learning rate, you need a minimal learning rate, and you need a maximum number of iterations. And these all interact with each other, right? So the schedule really is flexible, but you also need to tune it with standard HPO approaches to be able to solve your data set that you're interested in as best as possible, right? So while you get some flexibility, you always will have to tune particularly for the data set at hand such that you have the most efficient or most well-performing model in the end. If you do not know a well-performing analytic expression of your heuristic, what you could do instead is DAC-by optimization. So what you do there is you discretize your optimization problem into multiple discrete steps. So on a linear schedule, for example, you would want to tune your learning rate after 0 epochs, 10 epochs, 20, 30, and so on. Or on a exponential schedule after 0, 10, 30, and 90. And at each of these steps, you would have to tune your learning rate individually. So that means that after 0 epochs, you tune your learning rates. After 10 epochs, you tune your learning rate, and so on. But you would do this in a one-shot manner. So for example, just with your normal HPO, but treat these as individual hyperparameters. And while you might already get to some well-performing schedule this way, it might not be the most meaningful way of actually learning that. And in particular, a direct schedule has a few disadvantages. So the discretization, for example, is extremely important, and it's hard to optimize for a reasonable pattern. And these hyperparameters often do not depend, are not independent, right? So how you set the first learning rate should also inform how you should set the next learning rate, and so on. And you shouldn't have these erratic jumps up and down all the time. So knowing how the previous value was set should be also taken into account there, which is not the easiest in the direct optimization approach. Instead, you could learn a function of a schedule, right? Your policy would take some state as an observation and would be parameterized by some weights of a neural network, for example. And if you have that, well, we can observe the cost of a configuration using any black box optimizer, then we can directly optimize these weights, right? So in an evolutionary strategy style, you could find really well-performing policies in this setting and use them also for dynamic configuration. The next option is dynamic algorithm configuration by reinforcement learning. The nice thing here is that the agent is trained by means of RL in a purely data-driven fashion, right? So the policy of the agent observes the state of the algorithm. Based on this observation, it can choose an action which induces some change. The algorithm transitions for a few states. The policy sees the next state and the associated reward, right? And based on this reward, you can directly learn how to adapt your policy if that was a good choice or if it was a bad choice. So you reinforce good decisions and you learn to avoid bad behaviors. And the difference to optimization here is that DAC by RL can make better use of the sequential structure. RL is really one of the best sequential decision-making approaches, and it can leverage the structure very well. And like I said also earlier, you can have an easier time adapting your hyperparameters, for example, by directly taking into account how the previous hyperparameter value was set in this algorithm, how it transitioned, and so on. And this also allows you to find generalizing policies by conditioning on the data set, right? So we take into account that we have multiple data sets that we want to learn from, and conditioning on the data set means we also observe some features of the data set so that we can learn more general policies. To take home for you is that DAC generates reusable configuration policies. We do not just adapt, we learn a policy that can adapt across multiple data sets, right? This is very crucial to the DAC problem. And that comes in a variety of flavors. So depending on a choice of the solution approach, you can get very expressive policies, but also some policies that are already helping with configuration, but might not be as expressive because they might only be set up to adapt your hyperparameters every 100 steps or something like this.